Swayam Prabha. Digital India. Educated India.
Dear viewers, in this session, I would like to discuss the various methods of surface representation and analysis, so that the topographic related information can be extracted from DEMs. Digital modeling may be used to answer a variety of spatial questions by employing one or more of the following classes of analytical techniques: interpolation and surface fitting, creating new DEM data sets, extraction of topographic attributes and landscape features, and visibility and viewshed analysis. So, let us look at interpolation and surface fitting. Interpolation is the process by which elevation values of one or more points in the geographic space are used to produce estimated values of the positions where elevation information is required. It is used for contouring and for the generation of DEMs from selectively or randomly sampled elevation points. Interpolation may be computed by directly using elevation values in the DEM or TIN without the assistance of a surface fitting algorithm. In this particular graphics, a general nature of DEM and TIN is shown for the viewers before we proceed to the interpolation. Here in this case, in the DEM, a point M whose elevation is to be found out, and it is located somewhere between 3 and 4 and B and C in the row and column directions respectively in the DEM. Similarly, in the TIN, this particular point N is whose height is to be estimated lies within the triangle C, B, C and E. So, now let us look how we would do the interpolation. In the figure, for example, the estimated elevation values of the point M is designated as Zm and Zn in the DEM and TIN, and may be calculated as Zm is equal to Zb3 plus Zb4 plus Z3c plus Z4c divided by 4, where Z3b, Z4b and Z3c are elevation values for the grid intersections 3b, 4b, 4c and 3c respectively, and the value of Zn in the TIN model can be computed as Zc plus Zb plus Ze divided by 3, where Zc, Zb and Ze are the elevation values for the vertices C, B and E respectively. In practice, however, a surface fitting algorithm is commonly used to improve the result of the terrain modeling. The surface fitting algorithm may be linear or non-linear, depending on the order of the polynomial equations used for estimating the elevation of the required point. The general polynomial equation for surface fitting is given in the next table, where Z I is the elevation value of an individual point I, x I and y I are its coordinates, and a0, a1, a2 and so on are the coefficients of the polynomial. So, let us look at the general polynomial equation. It can be categorized in terms of the order or or it could be in a descriptive form. So, if z is only equal to a 0, then this is a 0 order polynomial, and it can be described as a planar model, and there are only one term in it. If we make this polynomial a first order polynomial, now it is representing a linear relationship, and two more terms are added, that is z is equal to a 0 plus a 1 x plus a 2 y. Similarly, the third order would have the next values to the polynomial, which is a 3 x square plus a 4 y square plus a 5 x y, and this would be quadratic in nature. If we keep on increasing the order of the polynomial, that is, we make it a third order polynomial, it would be representing a cubic relationship and so on. And as we keep on increasing the order of the polynomial, the number of coefficients keep on increasing. And what we can see is, for a fifth order polynomial, there would be about 15 coefficients or so, which would be taking into consideration the nature of the surface fitting algorithm. To find the values, elevation values for point M in the figure using linear interpolation, for example, the first step is to set up a set of equations to solve for the coefficients a 0, a 1 and a 2, such that z b 3 can be correlated to be having a mathematical representation of the form a 0 plus a 1 x b plus a 2 y b. The value z b 4 can be represented as a 0 plus a 1 x b 4 plus a 2 y b 4. Similarly, the elevation value of z 3 c can be expressed as a 0 plus a 1 x 3 c plus a 2 y 3 c, and similarly z 4 c can be expressed as a 0 plus a 1 x 4 c plus a 2 y 4 c. In this particular set of equations, we find that the number of equations are more than the number of unknowns, and thus a least square solution can be adopted. Once the values of a 0, a 1 and a 2 have been determined, the value of m can now be found out using the relationship z m is equal to a 0 plus a 1 x m plus a 2 y m, where x m and y m are known coordinates of the point M. This method of interpolation is known as the local approach. Local interpolators apply an algorithm repeatedly to a small portion of the total area in order to ensure a good fit. This approach of interpolation is conceptually simple and computationally easy to implement. However, since the interpolated surface value and consequently the fitted surface at a point depends on neighboring data, there is no consideration on the characteristics of the terrain continuity and smoothness in nature. The global approach of interpolation removes such a shortcoming of the local approach by utilizing all or most of the elevation data to characterize the surface at a point, thus allowing prediction to be made on the trend of the surface. The next figure illustrates conceptually the difference between the two approaches of interpolation. For the terrain point P, the estimated elevation of H1 when interpolated locally using only the values of the two neighboring points 3 and 4. If the interpolated globally using the values of the point 1 to 6 as shown in figure B, the estimated elevation of P becomes H2, which is greater than H1. So, here this particular slide shows the difference between local and global interpolation as being discussed earlier. The estimated elevation values of P will be the same in case of figure B and C if interpolated locally, assuming that the neighboring data points used in both the cases have the same elevation values. If the effect of the non-neighboring points are taken into account in global interpolation, the resulting elevation values of P in the two cases would be different. The examples of figure B and C clearly demonstrate that the estimated elevation value of a terrain point is affected not only by its intermediate neighbors, but also by those points that are located away from it. Therefore, global interpolation approaches obviously have the advantage of preserving terrain continuity and smoothness. However, as terrain modeling always involves a very large number of points, global methods are computationally very demanding. A widely used global surface fitting method is trend surface analysis. In this method, the terrain surface is approximated by a polynomial expansion of the coordinates of the sampled points. The coefficients of the polynomial functions are determined by solving a set of simultaneous equations, which include the sum of the powers and the cross products of x, y and z values by the method of least squares. This ensures that the sum of the squared deviations from the trend surface is a minimum. Once the coefficients have been computed, the polynomial functions can be evaluated at any point within the geographic space under investigation. Some of the commonly used polynomials are linear, where z is equal to a plus b x plus c y, or quadratic, where z is equal to a plus b x plus c y plus d x square plus e x y plus f y square, or cubic, where z is expressed as equal to a plus b x plus c y plus d x square plus e x y plus f y squared plus g x cube plus h x square y plus I x y squared plus j y cube, where z is the estimated height, x and y are the geographic coordinates, and a, b, c, d, e, f to j are the polynomial coefficients. The same can be now seen in the next slide, wherein a graphical representations of the three forms of trend surfaces so produced by linear, quadratic and cubic polynomial equations are shown. Trend surface analysis is also a useful data exploratory tool. It is a relatively simple to create a grid matrix of values by substituting the coordinates of the grid nodes into the polynomial and calculating an estimate of the surface for each node. The next method of interpolation is inverse distance weighted or IDW interpolation, which is a simple local interpolation method most commonly used. It is usually implemented in the form of a moving window to define the zone of influence. In vector based processing, a circular moving window is often used instead. This method is based on the assumption that the influence of each input on the interpolated value at the center of the window is inversely proportional to a power of p of its distance from the center as expressed in the following equation. Here the z can be correlated to be a summation of all those points contributing within that particular window and taking the distance between those point of investigation and the point whose elevation raised to the power p divided by the sum of the distances between the 2 points raised to the power p. Here z u0 is the estimated value of the point at an unsampled location, z ui are the data points, dij is the distance between each data point at an unsampled location and p is a parameter. Typically, p is equal to 2. In other words, the weights are inversely proportional to the squared distance between the data point and the point at the unsampled location. The quality of the resulting surface as indicated by the fitting between the surface and the input points is dependent on the density, distribution and accuracy of the input points. Here in this particular figure, we can see the representation of a moving window over a DEM having random sample points, and based on the point and its region defined by the moving window, the estimation of the unknown point is being shown. A shortcoming of this interpolation method is that it does not reproduce the local shape implied by the data and tends to produce local extreme at the data points. Just like trend surfaces, IDW surfaces seldom go through the input points. In other words, IDW is not an exact interpolation method. Finally, an optimal local interpolation method known as kriging, originally developed for ore reserve estimation in geostatistics, is now widely used in DTM software packages because it is flexible and can handle any type of data. So, let us look at kriging. Kriging, named after the pioneering work of Danny Krig in 1951, is a generic name of a family of least square linear regression algorithms that are used to estimate the value of a continuous attribute such as terrain height at any unsampled location using only attribute data available over the study area. Kriging treats the continuous attribute to be interpolated as a regionalized variable. In one approach known as simple kriging, it is assumed that the expected value of a random variable at a specified location, that is the estimate, equals the mean value in the study area. In this case, a virogram which represents the relationship between the mean square difference between sample values and their distances can be used to determine the value at the unsampled location. Mathematically, the virogram of radius 2r or semi-virogram of radius r can be defined as by the equation given below, where r is equal to n by 2 summation of I minus 1 to n z u I plus d minus z u I whole square, where d is the distance between the two sample points, z u I is the number of points in the study area, and n is the total number of data points available. The same is shown graphically in the figure drawn below. Another approach, known as ordinary kriging, assumes that the mean value is constant but unknown, and the local variation of the mean needs to be accounted for. The variogram may be used to determine weights needed for local interpolation. Due to the assumptions of simple kriging are not always realistic, another approach called the universal kriging with a trend model is used. This considers that the unknown local mean values varies smoothly within each local neighborhood and the whole study area, so that the local trend over the whole study area can be modeled by a polynomial function such as a linear or quadratic trend. The various approaches of kriging mentioned earlier estimates values at points. The resulting map based on the result from point kriging displays a lot of sharp spikes and pits at the data points. This may be overcome by estimating an average value of a block of land, hence the name block kriging. Finally, another useful approach to kriging is called co-kriging. At one sample location, data for more than one attribute may be available. If the data for each attribute are spatially correlated, it is possible to use the spatial variation of one attribute to help map the other attribute. This applies when the data for one particular attribute are more difficult or too expensive to obtain. Therefore, the other less expensive set of attribute data becomes the surrogate for the most expensive data set. Let us look at the other type of creating DMs using new DM data sets. An important application in the interpolation method explained earlier is to create a new DM data set from point data. A new digital terrain data are sometimes required because existing data may not be of a resolution or quality compatible to a certain application. The production of a new DM may also be warranted because of the availability of new source data. Instead of creating a completely new data set, it may be more economical to refine an existing DM by incorporating these new data. With the aid of interpolation using a surface fitting algorithm, a DM of higher resolution may be constructed from an existing one of a lower resolution. The next aspect of DM could be extraction of topographic attributes and landscape features. Topographic attributes, which are defined as numerical descriptions of the terrain, may be classified as primary or secondary attributes. Primary topographic attributes are those geomorphic parameters that may be directly calculated from digital terrain, such as elevation and slope. Secondary attributes, also referred to as compound attributes, are found by combining the primary attributes with other environmental indices that characterize the spatial variability of specific processes occurring in the landscape, for example, soil water content distribution. Of the primary topography attribution used to describe landforms, the following may be easily estimated from DEM data using automated methods. So, let us look at some of the definitions of the topographic attributes that we may be interested in extracting from a DEM. First is elevation, which can be expressed as the altitude or the height of the terrain point. The next is slope, which expresses the gradient of the land. Third is aspect, which is nothing but the azimuth of the maximum local slope. Specific catchment area, that is the upslope area draining across a unit width of the contour. Flow path length, that is the maximum distance of water flow to a point in a catchment. Then profile curvature, that is the curvature of the slope profile that we have, and then plan curvature, which is curvature of the contour. Having had a look at this, now let us look at the accuracy of the digital terrain models. The accuracy of a DTM is of concern to both DTM producers and users. For a DEM project, accuracy, efficiency and economy are the three main factors to be considered. Accuracy is perhaps the most single important factor to be considered, because if the accuracy of a DM does not meet the requirements, then the whole project needs to be repeated, and thus the economy and the efficiency will be ultimately be affected. The assessment of DTM accuracy can be carried out in two different modes, that is, the planimetric accuracy and the height accuracies can be assessed separately, or both can be assessed simultaneously. For the former case, the accuracy results for the planimetry can be obtained separately from the accuracy of these results in a vertical direction. However, for the latter, an accuracy measure of both error components together is required. There are four possible approaches for assessing the height accuracy of the DTM, namely prediction by production, that is the procedures used, prediction by area, prediction by cartometric testing, and evaluation by diagnostic points. So, let us look at them each one by one. First is prediction by production, that is the procedures used. This is to assess the likely errors introduced at the various production stages together with an assessment of the vertical accuracy of the source materials. The accuracy of the final DTM is the consequence or concatenation of the errors involved in all these stages. The next is prediction by error. This is based on the fact that the vertical accuracy of contour lines in a topographic map is highly correlated with the mean slope of the area. Next is evaluation by cartometric testing. This is about experimental evaluation. It is argued by many that the entire model rather than the node should be tested. For such a test, a set of checkpoints is required. The fourth approach is evaluation by diagnostic points. A sample of heights is acquired from the source material at the time of data acquisition, and this set of data is used to check the quality of the model. This can be conducted at any intermediate stage as well as at the final stage. There are three approaches for assessing the planimetric accuracy of a DTM, namely no error. It is argued that a DTM provides a useful set of heights with planimetric positions which are inherently precise. Then we may have predictive approach, that is similar to the prediction by area used for vertical accuracy through height to fix the positions of node heights by comparing a series of points. An alternative approach is to simultaneously assess the vertical and the horizontal accuracies. Now, let us look at the factors which affect DTM accuracy. The accuracy of the DTM is a function of a number of variables such as the roughness of the terrain surface, the interpolation function, the interpolation methods, and the three attributes accuracy, density, and distribution of the source data. Using all these variables, a function can be developed to express the accuracy of a DTM, which can be a function of the characteristics of the DTM surfaces expressed as C DTM, or the method used for modeling the DTM surfaces, that is M modeling, the roughness of the terrain surface expressed as R terrain, and the three attributes accuracy, distribution, and density represented by A data, D data, and DN data, and finally, scope to include any other source or cause which may have its role in the DTM accuracy expressed as O. The roughness of the terrain surface determines the difficulty of the DTM representation of the terrain. If the terrain is simple, then only a few points need to be sampled, and the surface to be used for reconstruction will be very simple. For example, if the terrain is flat, only 3 points are essential, and a plane can be used for modeling this piece of terrain surface. On the other hand, if the surface is complex, then more points needed to be measured, and higher order polynomials may have to be used for the modeling of this terrain. A DTM surface can be constructed by two methods. One is to construct it directly from the measured data, and the other is indirect. In the latter, the DTM surface is constructed from the grid data that are interpolated via a random to grid interpolation. The accuracy of the DTM surface constructed indirectly will be lower than the accuracy of the DTM constructed directly due to the accuracy loss in the random to grid interpolation procedures. There are three types of DTM surfaces which are possible: discontinuous, continuous, and smooth. It has been found that the continuous surface consists of a series of contiguous linear facets is the least misleading, or one can say the most trustworthy. The three attributes of the source data, that is distribution, accuracy, and density, will also have a great influence on the accuracy of the final DTM. If there are a lot of points in the smooth or flat areas, a few point in the rough areas, then the result will not be satisfactory. Aerial photographs and existing topographical maps are the main data sources for digital terrain modeling. The accuracy of the photogrammetric data is affected by the following factors. Generally, the accuracy of photogrammetric data is 0.07 to 0.1 h% if acquired by using an analytical photogrammetric plotter, or 0.01 to 0.02 h% if acquired using a analog photogrammetric plotter, where h is the flying height. It refers to the accuracy of the static measurements. However, if the measurement is dynamic, that is contouring and profiling, the accuracy is much lower. The speed of measurement is also an important factor. Various experimental tests reveal that the accuracy of photogrammetrically measured data is of the order of 0.3 h%. The accuracy of the contouring data obtained from digitization is affected by the following factors. First, the accuracy and the physical conditions of the digitizer. The second is the quality of the original map, and third is the accuracy of measurement. The accuracy of contours can be written as MC is equal to MH plus MP multiplied by tan alpha, where MH refers to the height accuracy of the height measurements, MP is the overall height accuracy of the contour, including the effect of planimetric errors. Usually, the accuracy specifications for contours all appear in the form of the above relationship. The summary of such specifications have been given in the table. Normally, when we look at the accuracy specifications for contours, we find that for different regions or for different countries, depending on the scale of mapping, the accuracy of the contours can be defined. For example, in France, where the scale of mapping could be at the level of 1:5000, the accuracy of the contours can be expressed to be 0.4 plus 3 multiplied by tan alpha, where alpha is the slope. In Switzerland, at a scale of 1:10,000, this could be 1.0 plus 3 multiplied by tan alpha. In Britain, where the scale is at 10,560, the accuracy of the contours can be expressed as under root of 1.8 square plus 3 alphas whole square. In Italy, it is 1.8 plus 12.5 tan alpha. In France, at a scale of 1:25,000, this is expressed as 0.8 plus 5 tan alpha. In Finland, it is 1.5 plus 3 tan alpha. In America, at a scale of mapping of 1:50,000, this is 1.8 plus 15 tan alpha, and in Switzerland, it is 1.5 plus 10 tan alpha. The accuracy loss during the digitization process is about 0.1 millimeter in point mode and about 0.2 to 0.25 millimeters in the stream mode. In any case, the overall accuracy of the digitized contour data will still be within a 1/3 contouring interval. So, now let us look at the different accuracies of DTM data as obtained by different techniques. So, if we are going for ground based measurements including GPS, then the accuracy of the data acquired could be of the order of 1 to 10 centimeters. From digitized contours, it is about 1/3 the contouring interval. For laser altimetry, it is between 0.5 to 2 meters, radar grammetry between 10 to 100 millimeters. In aerial photogrammetry, it is between 0.1 to 1 meters, and through SAR interferometry, it is between 5 to 20 meters. Having discussed the accuracy with which the DTM can be generated, the next thing to be considered is the software for digital data processing. In general, conventional GIS software is weak in DTM functions. Although geographic data are 3D in nature, practically all GIS softwares have been designed up to now are 2D data models. Digital terrain data are geographic data in every sense of the term, but they have specific requirements in terms of data structure, processing procedures and the methods of information presentation. Software used for digital terrain data processing may be divided into 4 categories according to their designed function, that is terrain model construction, functional extension to GIS, terrain data visualization, and 4th is contouring. Now, let us look at the application of digital terrain models. Well, here if very small list has been taken into consideration, reason being because every spatial data on the earth's surface has to have a ground representation. And here in DEM, we are trying to project the same data having a spatial context in a numerical format, so that it can be displayed and assessed. So, some of the key application areas are the hydrological and geomorphological, geoscientific applications, engineering applications, and natural resource management applications. Hydrological and geomorphological applications. Since the middle 1980s, there has been an increasing recognition of the need to predict spatially variable hydrologic processes at a fine resolution. This has led to the era of spatial modeling in the science of hydrology. Digital terrain data and remote sensing catchment characteristics, that is vegetation cover, are now considered as crucial data input to the new generations of hydrological and water quality models. Different forms of digital terrain data, that is DM based or tin based or contour based, are used in different models to provide the spatial component of the analysis. In geoscientific applications, the impact of DTM on geoscientific data processes may be explained from 2 interrelated perspectives. First is data management and integration, and the second is data analysis and visualization. So, let us look at data management and integration. Geoscientific modeling usually requires the use of the data from a variety of sources. Many applications require non-standard solutions to database access and 3D representation because of the range of data types, collection specifications, spatial data structures and access keys, as well as the complex geometry of the subsurface domains. The adoption of GIS and DTM techniques appears to have provided the data structure and data management tools for the formulation of a more unified approach to geoscientific data processing. It has also provided the mechanism for integrating data obtained in different ways at different scales and with different cartographic specifications. Data analysis and visualization. Manual processing and analysis of data represented a major constraint in geoscientific investigations in the past. Individual geoscientific data sets are characteristically incomplete in nature. The creation of graphics from numerical data is both time consuming and error prone. The ability to rapidly create and retrieve and integrate geological, geophysical and related topographical data allows geoscientists to understand the surface and subsurface environments by collaborating information from different sources. By using true 3D visualization techniques, sometimes in the real time or near real time situations, the ability of the geoscientists to analyze problems and develop solutions may be greatly increased. Now, let us look at some of the engineering applications which could be there. The three major applications that can be identified for engineering applications of DTM are design, analysis including computations and visualization. Design. In engineering projects, contouring is the perfect method of checking irregularities and the smoothness in design surfaces. The objective of DTM is to identify the geometric skeleton of the engineering design and to create a combined horizontal and vertical alignment strings that define the major feature or structures. Analysis including computations. DTM software packages, particularly those developed for engineering applications, contain a range of functions for the analysis of terrain data. Typical functions may include calculations of area, volumes, slopes and aspects, generation of longitude and cross sections, computations of testing out information, triangulation of surfaces and contouring, and finally, delineation of watershed and viewsheds. The third is visualization. This function allows the engineer to evaluate the design before it is finalized. Both wire line and hidden line perspective views can be used. More sophisticated packages allow the draping of image data to produce photorealistic views. The use of visualization is particularly popular in road design. Many highway design systems now incorporate terrain visualization capabilities. In this slide, we can see a 2.5D visualization of the terrain using a wire frame to show the variations of the ground. However, if this is draped with a aerial photograph or satellite data, the real world picture now emerges, wherein the ground feature information is now draped over the digital elevation model, and now one can understand the correlation between the ground features and the ground elevation. And this is very critical, specifically when engineering based applications have to be carried out. So, with the development of powerful computer graphics softwares and hardwares, three-dimensional terrain visualization also has become possible, superseding the 2.5 dimensional visualization. In this particular slide, we can now see a DEM with a bridge connecting two different bank lines of a river and the manner in which the bridge has to be constructed. This is the ultimate target that a engineer or a planner is interested, so that even before the project is completed or is initiated, he has a very specific idea as to the layout of the engineering elements. In natural resource management, DTM plays a significant role in terms of planning and management. As the relative magnitudes of many biophysical processes that occur in the natural landscape are sensitive to topographic characteristics such as slope and aspect. Digital terrain data are central to climatic and biological modeling pertaining to natural resources. DTM in this particular domain may be applied at a global or local scale. It may also be applied in the operational environment as well as in the predictive modeling stage. In the past, these applications were seriously hampered by the lack of digital terrain data. With the increasing availability of global and national digital terrain data, biophysical models for natural resource inventory, analysis and planning may now be developed using landscape processes as a basis. In my next session, I would like to now introduce the technology of GIS. Thank you.